There is a substance on Earth so lethal it sounds like science fiction. A single drop, bypassing your body's defenses, can end your life. That substance is polonium, specifically the isotope polonium-210, sitting at number 84 on the periodic table. It's an extremely rare, highly radioactive element, first isolated in 1898 by the physicist Marie Curie. She and her husband, Pierre Curie, discovered it while analyzing uranium ore. To understand its physical power, look at this comparison. Gram for gram, polonium-210 produces a massive amount of heat entirely on its own, driven by the rapid decay of its atoms. A tiny sample sitting on a desk will actually become noticeably warm to the touch. This continuous output of raw energy makes the element fascinating to researchers and incredibly dangerous to living things. If you browse enough videos or articles online, you've probably heard a very specific claim. If you touch polonium, you will die instantly. But physics tells a different story. Pure polonium cannot kill a person the second it brushes against their skin. It releases high-energy alpha particles. They carry tremendous force, but cannot travel far, stopping when they hit a single sheet of paper. Your body has a similar defense. The outer layer of your skin blocks these exact same particles, creating a biological shield. So we arrive at a contradiction. If basic physical barriers defeat polonium so easily, why do toxicologists universally classify it as one of the deadliest poisons ever discovered? The answer comes down to geography. Outside your body, the element is manageable, but the moment that radioactive material moves past the skin, the biological shield becomes irrelevant. The danger begins when the physical threshold is breached. If microscopic particles of polonium enter through an open cut, get inhaled as dust, or are swallowed, the threat is no longer external. Once inside the bloodstream or lungs, your internal organs have no armored outer layer. The living cells are left completely exposed. Without that physical barrier, the alpha radiation acts like millions of microscopic bullets firing directly into soft tissue at point-blank range. These heavy particles tear through cellular membranes and physically shatter your DNA strands. Once the DNA breaks apart, the affected cells lose their ability to divide and repair themselves. This cellular death triggers a rapid cascade. Tissues decay, and the organs quickly begin to fail from acute radiation poisoning. Reflective. Radioactive contamination destroys at the cellular level, causing catastrophic damage from inside the body's primary defenses. The devastating reality of this biology was proven in 2006, when former Russian intelligence officer Alexander Litvinenko was assassinated in London. Medical examiners concluded his death was caused by ingesting a microscopic dose of polonium-210 slipped into his tea. Because alpha radiation is highly energetic, investigators were able to map his final days by tracing the radioactive path he left across London. Tracking that microscopic threat required specialized detection equipment to pick up the specific alpha decay signatures left behind. Litvinenko's death demonstrated how a single speck of this element, successfully placed on the wrong side of the human biological barrier, functions as an unstoppable weapon. If an element is this volatile and unforgiving, how do modern researchers study it without putting their own lives at risk? The solution is absolute physical distance. Scientists handle the material using precision robotic arms to keep the element far away from their own bodies. They operate these tools from behind heavy lead shielding and thick observation windows designed to block alpha and gamma emissions. Even the smallest microscopic samples are carefully lowered into massive, heavily sealed containers for storage. Modern chemistry involves discovering potent natural forces, but it requires engineering rigorous physical systems to manage them. And when those extreme safety measures are in place, polonium is actually highly useful to society. In controlled industrial settings, tiny amounts of the element are used in specialized machinery to eliminate static electricity during manufacturing processes. The same heat-generating properties found in radioactive decay are applied to radioisotope thermoelectric generators to power deep space missions. In medicine, researchers study alpha emitter therapy to destroy cancer tumors while sparing the surrounding healthy tissue. When we separate the actual physics of an element from sensational internet myths, we replace pure panic with actionable knowledge. We do not need to fear chemistry. We simply have to respect it. Respecting the mechanics of the smallest atoms allows us to turn a lethal poison into a tool for exploration and healing.